Let's take an example of some interference. We're going to look at some problems here, or well, one problem, sorry. And we're looking at two uh, waves that are traveling down a cord or a rope. One's moving in the right direction and one's moving in the left direction. And I actually forgot to put a minus sign in here for the second one. So we'll put that in here. So I have these two equations for the waves that are moving right and left, and I want to find the interference. Well, the interference as a function of x and time is just going to be equal to d right x comma t plus d left x comma t. Now you could do left first and then right. It just really depends on which perspective you want to look at, but I put d right first. So that's equal to 0.35 meters cosine of 0.4 pi per meter minus 10 pi per second times t plus a negative 0.35 meters cosine of 0.8 pi over 1 meter times x plus 20 pi 1 over s times t. And we can simplify this a little bit. We can pull out the 0.35 meters, and that leaves us with 2 cosines. Let's see, 0.8 pi per meter x plus 20 pi per second times t. Now, I'd like to get rid of these cosines. I have a cosine of some angle minus cosine of another angle. So how can we simplify this? Well, if we look at the trigonometric reference, you'll see the identity right here. And so I'm going to rewrite that on my slide here. And I'm going to rename the variables a little bit. So we have cosine theta 1 minus cosine theta 2 is equal to negative 2 times sine of the two angles added together divided by 2 times the sine of the difference of the angles. And now adding in our two equations that we've identified. So we're going to have a -2 times the 0.35 meters times the sine of, we're going to have 0.4 pi x minus 10 pi t plus 0.8 pi x plus 20 pi t, and this is all going to be over 2. And then we'll do the sine. Minus, this is just a lot of writing. Make sure you don't mess up. I have a tendency to do that. Hopefully catch all of them. Divide this all by 2 and have a bracket at the end. And then this will just simplify down to -0.7 meters times sine of 0.6 pi per meter times x minus 5 pi per s times t times the sine, and we're going to have -0.2 pi per meter times x minus 15 pi per second times t. Now this type of formula is also common in other applications, not dealing with interference, but using the concepts of interference. You can actually transmit data from point A to point B using electromagnetic waves. So this is a common formula. It's called amplitude modulation, and we'll discuss a little bit more about that in a future video. Now let's look at the graph of all three of these equations. So the red is our wave going to the right, the blue is the one going to the left, and the interference is the green. Now notice that when the amplitudes are at the same peak, the what happened to my picture? There we go. Guess I deleted it. Sorry. So when the peaks match, you see that the interference peak is the addition of those two. I don't know why my program is giving me all these dings, so I apologize. And when the amplitudes are opposite each other, notice that the amplitude of the interference is at 0. So you get this pulsing with this type of wave. You get this pulsing between. This is just a snapshot in time. So this interference is interesting because you can look at and find where these peaks are at in the same phase, which means just in the same direction, same angles. And you can also see the effect where you have interference, which is constructive. So this part these are constructive. My computer is going to give me a problem here. Alright, well, these huge peaks here, the double, where you have the two peaks of the two waves meeting up, that's constructive. Whereas where the peak goes to 0, that's destructive. So this is a good example showing the two different forms of interference, constructive and destructive interference.